gluttons for punishment, I guess. So this is going to be basics. If you've had a statistics course, this is going to be review. We're not going into a whole lot of detail. A big thing for me is I want to make sure that if you're reading the articles where we put some statistical values in, that you understand what we're actually saying and you can make some interpretation on your own. So why do we need statistics in research? A lot of the original statisticians, of course, would have been mathematicians. So they used math and models so they could evaluate data sets to prove whether or not that they're different. Well, not prove, but see how confident are we that these data sets are actually different, that we don't have the same results. So this can be anything from soil nutrients yields to crop height, anything that we want to compare and show that we actually had a difference, whether it's from our treatments or if it's just from natural variability that's out there. So one of the terms I'm going to use is the word population, which is a statistical term. I've never liked the term because it reminds me of people and the planet. But population is, I like people, perfectly fine. I'm just saying I don't like the term. So they're known as different populations, and we want to prove whether or not these populations are different. So I'm going to use the word population a lot, and I'm going to show you curves like this. And you have to understand what this curve actually is. The higher it is, this is just the frequency, how many times you made that observation. So if this is a field that has an average yield and it has a high and a low yield, you have more yields in the middle, so it stacks up. Think of just stacking these yields on top of themselves. So all these curves, this is not yield up on the side, the value's at the bottom, and we're saying we have a lot more yields in the middle. So if this is 150, this could be 150, and this is 150. It's just how many stack up. So this is the frequency. So when we talk about population, it's all the potential outcomes of whatever you're looking at. What's your question? And it could be every possible corn yield in one field. It could be every possible corn yield across the entire planet. Those populations and how many sampling points you would need from that, that's where the difference comes from. Because the larger your question is, the harder it is to actually get a good idea of what's going on out there. It could be you have rainfall amount in the season. It could be just disease in one county in Delaware. It could be anything like that. So the way to describe a population is there's typically two values that we look at, assuming that your data is normal, which I'll go over, and that is the mean, which is the average. You guys know how to make an average. 10 plus 20 plus 30 divided by 3 is an average of 20, right? That's an easy one. Corn yield in this field, it might range from 100 to 200 bushels. Your average is 150. You'll see, remember, this is that frequency. A whole lot of them happen here in the middle. So most of your yields are probably between 140 and 160 with a few on the edge. So they'll all average out to a certain value. So that's one thing that we use. The other one is the variability. And the mean and the variability together, they're what help us determine whether something is different from something else. So variability is you take that average and you take every single yield and you subtract it from the average. So if this is your average right here, everything on this side subtracted from the average should be positive. Everything on this side should be negative. And because we want to know the overall difference, they square it. So you make that negative value positive. So you can add these together and say, well, this is the total difference on both sides of that average. And that's your variability. If you look at these three curves that we have here, the green one has higher variability than the orange. If you look here, every single one has the exact same average. They're all lined up down the middle. This one has greater variability. You see how high this green one is here? That means there's more values on that end. To have greater variability, you don't have to have a wider range. You don't have to go from 50 to 1,000 bushels in a field. You just have to have more values on that end. Because if you have more values and you subtract from the average, you're going to get a greater variability. So remember that with variability, it doesn't necessarily mean a wider range. It might just mean more points out at the edge. So standard deviation is the square root of the variability because you don't want to give people numbers that are squared. It doesn't always make sense to them. So we square it to get rid of that negative number, and then we take the square root to give you a standard deviation. But standard deviation and variance are pretty much derived from the same value. So here's an example distribution of yields. These are not real. I just made up numbers on a picture. But here's some plots we have here. 62, 51, 49 bushels. Add those up, average amount. It comes to 52 bushels average. The range we have in this field is 38 to 72 bushels with a standard deviation of 7.4. So you just do those calculations. And that describes all these plots here. So if you want to compare these plots to these plots, you do that same value, and you hope that these are actually coming from the range that you would expect from that treatment. And the good news is, if you have enough samples, in most cases it does. What statisticians figured out when they looked at all these different data sets is that there's a normality across the planet in a lot of the data. It follows what they call a normal curve, which means that they saw that in a lot of different data sets, from crops to medical histories to tree heights, anything, that within one standard deviation, 68% of the possible outcomes fell within that. Within two standard deviations, 95%. So you only have 2.5 on the high and low on either side where you could possibly sample something that's really far out on that curve. So if you take a sample of any field, what they're telling you is more than likely you're right here in the middle. There's a really good chance that you're close to that average. And the more points you sample, the more points you take, the more than likely that if you average those together, you're representing what's really going on. Because the problem is we can't sample every single possible outcome in any study. A lot of times we don't know every single possible outcome. So populations, that word population means every single possible yield that could happen under whatever circumstance you're looking at. But we don't know what that is. We can't sample it at that rate. So if you're in a field and you want to know heights of corn, maybe you just sample 100 plants. There might be 100,000 out there, but you say, well, I can measure 100 of them. So you measure 100, and if that's enough, and your data's normal, they probably fall in the middle, and that average, it might not be perfectly what it normally would be, but it will be close enough. But you need enough samples to do that. So in this case, if we took, say, 12 different plots, they could fall over this same range. It's not every single red dot that you saw before. That average won't be exactly in the middle, but it might be just to the left or just to the right. And the closer it is, and if you kept taking these samples at different times, year to year, you would get a slightly different average. If you sampled every point, you would get the exact average. So in this case, if you have 250 bushels, you have a standard deviation of 5 bushels in here. You can only make 12 plots of that hybrid. The average and the variability of this should be close to what would be there if you sampled every single one, as long as your data is normal. However, you have to take what we call a representative sample of the outcomes. And as your knowledge as an agronomist or crop scientist, you should know where bias would exist. The problem is when you don't know. So in this case, if you were to sample a field in a wet year and say that that represents all the possible outcomes in that field, you would end up with an average that's much lower than 250, and it would be incorrect. And if you were trying to compare this to something else, if you only did 1 year's worth of data, then you wouldn't be able to find a difference if there was one, or you might show one where there wasn't a difference. Now, your knowledge would say, I need to sample that field over several different years. But what if it's something you don't know about that's going on in that field? So here's something that's easy to think about. This is an image available online of every single mapped center pivot across Delmarva. So let's say you had a question was, I think that the number of 4 tower pivots is greater than the number of 3 tower pivots. Well, there's a finite number of pivots in Delaware. You could possibly measure every single one over a year if you wanted to, and then you wouldn't need statistics. You could show there's this many of 3 and there's this many of 4. You would have the entire population. If that's a lot of work, you subsample. Say in each county, you say, I'm going to look at 20 fields or 30 fields per county, and if you did a good job, then falls in that normal curve, those averages are probably close enough. And then we use statistics to determine whether it's different. My point is going to be, it's the size of your question. Let's say you're like, well, I want to say that there's more 4 tower pivots in the US than 3 tower pivots, and all you have is access to Delaware data. Well, you better hope that Delaware is representative of the entire country. If you really want to prove that, you would have to get a much larger data set. So the question you ask is important. So when we get into an ag question, and a lot of this will make sense, but you just have to think about it. Potassium rate for maximum yield. We're going to choose one crop. That would make sense. But what if you didn't? What if you're like, I'm going to figure out the potassium rate for maximum yield of every crop on the planet? You couldn't sample enough to get that. So you choose your crop. I'm going to do corn. But then you have to think about what's your soil type, because soil is going to have an effect. Choosing, if you put one plot per different soil type, you're going to have such different results you couldn't prove it. What's your weather going to be? What's your timing? So the more specific your question is, the easier it is to shrink that population down. All those outcomes get smaller, so you need less samples to look at. The problem is, and you see this with scientists a lot, you can only answer one question, and they hate that, especially if you're a graduate student working under a PhD advisor, and they're going to be like, let's figure out 30 different things with 5 samples. And so this happens a lot. We want to answer all of your questions in a year, but it can't be done. So it's better sometimes to just realize that you can only come out here and show you one outcome from one situation, and over your career, you build up this data set like we have in some cases. Same thing with cover crops and soil nitrogen. Well, what cover crop are you going to plant? Legumes only, mixes, grasses? What's your planting rate? What's your soil type? The more specific that question is, the more likely I can stand here and give you a good answer. The broader I make that, the harder it is for me to stand up here and give a good answer, even if there's differences. So for me, the more specific the question, the smaller the sample size. So my point is, if you're going to do some research, just know that if you decide to try to answer everything about one crop in 1 year, it's going to be very difficult to do. And then there is unknown bias. What about the things that you don't know that are affecting the outcomes? The good news is, again, if your data is normal, that whatever samples you pick should fall within those standard deviations, that 1 or 2 standard deviations. So if you take enough, if you only take 2, you might end up out here. If you take 12 or 50 or 100, you start to gather all those ones in the middle, and you're more likely to have a good average. But let's say you only do 2 plots. If you're lucky, maybe those 2 plots are in the middle, these 2 red dots. The variability is not right, but the average would be. Or you don't think about it, and you sample a very wet field, and you end up with very low yields, and those 2 are close together, and you say, well, it's very low. But it doesn't represent everything. Same thing if you only chose 2 here. If you chose all of these, maybe you get a better average. The good news is, as long as your data is normal, in most cases you're probably in the middle. But you can see that the less samples that you take, the less replication you make, the harder it is to get to that real average that's out there. So let's say you do a fungicide trial, and your populations are actually different. So in this field, you have 5 treatments. 1 was here in the middle, but you had enough here to put an average here, and these average there. And so using statistics, we can actually show, okay, you had an effect. So that's when we're talking about populations. If you increase the yield for real, and you've increased the average, you've created a new population that's different than the other one. So the question is, can we prove that they're different? Because what if you had some bias you didn't know about, and in this trial, you only sampled the lowest possible outcome with fungicide, and in this one, you sampled the best possible yields where you didn't put out fungicide. Statistics might show you that those aren't different when in fact they are. Again, if your data is normal, more than likely you're in the middle, but you have to think, how do I set up this study? How do I account for variability that I can't control? Or, this is 2 different populations. In this case, all these yields are the same. It doesn't matter whether you apply fungicide or not. But in the no fungicide plots, you put them all in a very wet spot and didn't think about it, or you didn't notice, or you weren't out there when it happened. And this one, you put on all the good soils, you would have very good and very bad yields, even though they're actually all the same. There was no effect of that fungicide. So how you sample is important, and you can set up the study very well, but then how do we analyze it? If we don't know, how do we know? You can't test every possible instance or combination. And what statisticians figured out is they looked at what are the possibilities, and they figure out what is the possibility that this wouldn't happen. What are the chances with this data set that there's only a 5% chance that this would happen? And then that's where we start. We never say with 100% that they're different. We say, man, there's only a 5% for this number to exist. And then we start to say, okay, if that's good enough for me, if 5% error is good enough for you, then it's different. So there's 2 analyses that we could talk about. One I will not. It's the t-test, because we don't use it a lot in agriculture. The ANOVA, the analysis of variance, works better for more than 2 treatments, which is typically what we do. We're going to have 5 rates of something, or several different seeding rates, fertility rates. We're going to look at several treatments, 5 N rates, 3 seeding rates, so it's more common for us. And ANOVA compares variability between all of your different treatments. Whereas a t-test compares the means between 2 things. So you see this a lot in the medical community. We can do it, but often we want to find out several more things in 1 year. The math behind these is very similar. The results and how you look at the data is very similar. But ANOVA is what we use more often in ag, so I'm going to talk about it. So ANOVA means analysis of variance. It uses something called the F-test. And the F-test looks at the variability between the means and across the entire variability within each treatment. So how large is the variability of all the data? So here's a possible treatment that we have, a study with soybeans. Again, made up numbers. We have a control where we did nothing. We got 56 bushels per acre. We added 30 pounds of K. We got 62. We added 60 pounds. We got 64. So you could look at that and say, well, there's a 2 bushel increase. But if you look at these averages here, we have a really wide variability down here at 56, 62, and 64. Are these different from each other or not? And what the F-test does is it takes all of these averages and it compares them to each other. That's the top, the variability between the means of each of your treatments. So the further apart those yields are, the bigger this number gets. And then the total variability within each treatment. So it looks how wide is this, how wide is this, and how wide is that. So if you have a lot more error in each treatment, this really wide one right here is going to make that bigger. The closer this value is to 1, that means those 2 variabilities are similar, so we say we can't prove that it's different. But if you look right here, the bigger this number is, so if you have a big difference in yields, this value gets larger and it's easier for us to say we're confident if these variabilities are that different, then they're not the same. And we can say that potassium addition worked in this case. So here's another way to look at it. You line these up. They have all very similar variability, but you average these 3 together and they would come down the middle. You subtract them from that. That number gets really large. And then the denominator down here, this is where a lot of our error comes from. If you don't do enough sampling down here, even if this mean is correct, if you have a really wide variability because your sampling wasn't high enough, it ends up making this term smaller overall and closer to 1. I'm not giving you the equations for statistics because they can be very difficult to look at and read. There's something else we do with the F value, and we divide that variance by degrees of freedom. Degrees of freedom is another statistical term that you can just relate back to how many treatments did you have or how many replicates did you have. So that variability in the top of the F value is divided by the number of treatments. So if you keep increasing your treatments, you make that top number smaller. Now that the way they sum up can get large, but if you keep increasing your treatments, you make that top value smaller, so it's harder to prove. Same thing down here with the denominator. If you increase your replication, you can help shrink that denominator, and then you can make this F value more likely to be larger. But all degrees of freedom are is their term, number of values a statistic is free to vary. So the more replication you have, the more degrees of freedom you have. What they figured out with all of this is they've looked at, mathematicians came up with what they call an F distribution, which means what are all the potential outcomes from using this equation. Without your data, just what are the potential outcomes and what are the chances that this number comes up. So to have a value close to 1 where they're not different is going to be down in this range, but what's the chance that you have a very large F? Because remember, the larger that value is, the more likely you have differences, and it shouldn't fall in the same distribution. So you see these numbers like 5% or 1% or 0.001%, and all they're saying is that F value is so large that it's out here, and it's unlikely to occur. There's a 5% chance that that value could occur. And so they have these tables, which if you take a stats class, you'll have to look up. I don't need you to understand the table. I need you to look at this F value. Up here, if you only had 1 replication and your alpha is 5%, which means we're looking to see if there's a 5% chance that this F value could exist. If you only have one replication, that F value has to be greater than 161. By 9 replications, it only has to be 5. So the way these tables are set up, they reward you for more replication. The more replication you have, the smaller that difference can be between yields because we have more confidence in it. But what you will see, because you're not going to be looking up tables, you're going to be given these values. You might be given something that's called the F value or the P value. So it's the probability that the F value could happen with this data. The chance you are wrong if you say there was a difference. So if someone says that it was significant at 5%, it means there's a 5% chance that I'm wrong. Is that okay with you? Would you rather have a 0.01% chance? Would you be comfortable with a 20% chance? It really depends on what you're looking at. If you want to know if there was an increase, if there was a product that was cheap enough to add and there's a 20% chance that the data is wrong, maybe you add it anyway. Scientists, we really like to be sure, so we use 5%, we use 1% differences. So for an example, let's say you added manganese starter to corn, you do the statistics, your F value has a 5% chance of existing. So what that's telling you is that number is so large, there's only a 5% chance that it would happen. So the manganese, we can say we think manganese increased yield in this case. But there's always a 5% chance that me saying that is wrong. And what are you comfortable with? A lot of times we report those values directly. What's nice with statistical software, and oftentimes what you'll see us actually give you, is the actual probability. So here's your F value from a study. Remember, the closer it is to 1, the more likely it's not different. So down here with our treatments, it's less than 1 at 0.58, 56% chance of that number existing. It's a pretty good chance that they're all the same, is what it's saying. Versus up here with our blocks, 0.006. So the reason I like it when they actually report an F value is you can make your own decisions. So if you look at a table like this, these 5 different treatments of seeding rate, and we're looking at some NDVI over wheat, if you get these F values, instead of someone saying it was significant at 0.05, you can actually look across here, and if they tell you it wasn't significant, you can make your own decision. So yes, this is not significant at 5%, but if you said, well, I'm comfortable with 20% chance I'm wrong, if the product is cheap enough, if it's easy enough to implement, and you're okay with the 20% chance that you're wrong, you can do it anyway. It can be a decision that you make. For us, we're never going to get up here and say it's okay. We always like these really low values so we can be certain of the difference that we're looking at. So this one, 0.7%, 0.01%, there's a difference. This one, at this point, it couldn't find a difference, 21%. The problem with ANOVA is it just analyzes the variances. It just looks at the differences in the variances. It doesn't tell you if each individual treatment is different. So they have these things they call Posthoc Tests. So these are other terms you might see that we report in any of our articles. You might see words like the Fisher's LSD or Tukey or Duncan's or Dunnett's. These are ways that we look at the ANOVA after we've decided, yes, there's a difference, and then it analyzes it at a certain alpha level. So back here, you can make a decision, 21% or 0.01%. At this point, to actually decide whether there's a difference, we have to tell the stats program, we want to see if there's a 10% error or a 5% error or a 1% error. In this case, this data is based on 10% chance that I'm wrong. And these letters along here, A, B, are how we tell you whether those treatments were different from each other or not. If you only have 2 treatments in a t-test, it's very easy. One was either higher or not. When you have 5 treatments, 2 of them could be similar, 5 of them could be different. It all depends on how close those averages were. So in this case, you can't see the red letters very well. If you see the same letter in any of this up here, that means they're the same. It doesn't matter. A versus AB doesn't mean that they're different. If you see an A anywhere in here, that means at the 10% level, 10% error, we can't say that those are different. We won't say that they're different. However, this one that's a C is definitely different. A versus C. 0.19 versus 0.17, we feel comfortable saying that there is less than 10% chance of being wrong about that. Whereas here, where you have a BC and a B, these two are the same, and these 3 Cs are the same. So the BC doesn't make a difference. It's the single letter. And what you can sometimes see, what's a pain, is if someone makes 10 treatments, you can have things that say A, B, C, D, E, and A, B, C all lined up, and it gets very, very difficult to tell what's going on. This is why I like less treatments. But once you see that, it's almost, to me, sometimes it's useless to report those. It's hard to decipher what's going on. So besides the ANOVA, there's two other things I can talk about. The numbers you might see in our articles. One is correlation, and we always remember, right, that correlation doesn't equal causation, and this is great data to talk about it, because we have potassium in the tissue versus yield. And these are just sampled across the region. This is real data. So this R squared right here, a 0.41, it's the proportion of yield that's explained by potassium in the leaf tissue. So what it's saying is it's positive, so they increase together. Yield increases as potassium increases in the tissue. 0.41 is how much is explained. 41% of that variability is explained by potassium. However, if you look over here, same data, 0.74, and it's negative, is explained by aluminum. So your yield drops with aluminum. So this says 41%, this says 74%. So when you look at these numbers, you always have to remember that correlation doesn't equal causation. Things can increase or decrease together for no reason at all. It's just circumstance. But this is one way for us to look at our data sets and put it out there for you. So never look at this as some kind of silver bullet that explains everything. It's just one variable, one way we can describe data. Regression is how we predict the relationship. This is something you probably have done in a math class in high school or college, where you create that y equals mx plus b type of equation, which you can do in Excel. And it will do the same thing. It will compare how far apart all these different yields are from an average line across here. But the nice thing about this is we can predict potential values with this. It's like what we do with GreenSeeker. We have an equation that says if your NDVI is this, the nitrogen you should apply is this. Whereas correlation just compares the direction, is it positive or negative, and how related it is. Regression is a way for us to create an equation to make a prediction, to help predict what might happen. So a lot more of the studies that I end up doing are ANOVAs because I'm comparing treatments, but this is another method that we can use to compare. This is used a lot in what we call observational studies, where we don't set up treatments, but we just go across a region and collect samples, where we didn't try to control anything, we just see what was going on. There are two types of experimental design that I'll talk about that you might also see in our publications. One is the completely randomized, and the other is going to be the randomized block. Here's some treatments we actually set up at Carville. It's 4 different treatments, different boron applications with 6 replications. And what I want to show you here is that you can randomize your plots and have the same number right next to each other. Sometimes people get confused. When they try to set up randomized study, they're like, well, I can't have 2 1s next to each other because it's not random. Of course that's random. Once you introduce bias and try to separate these, then it's definitely not random. So we stick these into Excel, into a random number generator, and let it put the plots where it wants to. So in this case, because we had so many replications, you're going to end up with plots right next to each other. A couple 4s next to each other, a couple 1s, and a couple 2s. But it's still randomized. The problem is, what if this is a really wet spot in the field and you have a whole bunch of number 4s, treatment number 4 right there? Another one you can use, and we use a lot, is a randomized block design. And it's supposed to create blocks across the field that try to make sure that all the treatments are in a certain area so you can account for that in-field variability. So in this case, if you look at this block, we have 4 treatments here, all 4 are in this block, but they're randomized, 3, 2, 1, 4. And then this block, 2, 1, 3, 4, 4, 2, 1, 3. So if you had a really wet spot down here, if you completely randomized it, it's very possible that all of your treatments for one group could be down there and you would throw off your values. So a lot of times what we block, because you know when you go across a field there's variability that you can't control. So if you block it, you make sure that every treatment is somewhere in that field so that you can get that average response. So you got to be careful when you're given certain graphs and you're given certain data in certain formats, like this one right here. These are soybean yields, and you can see treatment 3 really looks like it has a response. But of course, that scale there is only 58 to 63 bushels, so that's only a 2 bushel difference between some of these. So it's not a big difference. Not that we can't prove it's a different. In this case, it's not. It's that same data I showed you before. The blocks here were significantly different. The treatments weren't. The nice thing about blocking is statistics takes that error from the block to help remove it. So if you do have treatment differences, it does help you prove if they're there. All this really shows me is that fields at our research station are wet. And when you block across there, we definitely should have blocked it. This is saying, yes, you had a difference in those different blocks. That's what it's saying. So we have variability in that field that we have to account for in the next study. So statistics can be disappointing, but very helpful for the rest of us. We're the same as anybody else. We know sometimes when we put results up, people don't like it. We don't like it when we spend a whole summer growing a crop and not find a difference either, especially when we're looking at treatments. But you always have to remember is it's always an answer. It might be wrong. If we set up the study incorrectly, maybe there's a difference that actually should be there that we didn't find. But when I have a study that comes out at the end of the year and there's no differences, it's still an answer. It says that practice doesn't work, don't use that practice. And sometimes when you set up a research project and you're looking for an answer, you can lose track of that. You can forget that not getting a result is still a result. It's the truth of what's actually going on in that field. So if you look at this same study that we were just checking out with these different blocks, that treatment 3 that was so high, you have 63, 62, 72 bushels, 67, but you look over on this corner of the field, we had 49 and 54, which kind of drug it down. So if we hadn't blocked this field, it might have randomly placed more of the plots down this way and averagely inflated that yield and shown a difference that didn't exist. So this is the nice thing about blocking. Again, maybe there is a difference in the treatments I set up. Maybe what I needed to do was replicate this thing 30 times to find it because the field variability was too high. But by blocking it, I can feel more confident at least that the field variability didn't count into it. And I can come back to you and say there wasn't a difference and feel confident in saying that. So I think I went even faster than last time, but that's okay because you guys are ready to go home. Statistics in crops production, we can't sample every possible instance. That's what I was trying to point out to you. When they talk about population, we can't really know what it is. We have to take a subsample of that. And how you set up that study or how someone else sets up that study that you read is very important. It's hard to get that information sometimes. It's not out there in every single article. How is it set up? So we can estimate it if we take enough samples. Remember, everything, if it follows that normal curve, and we didn't talk about non-normal data or non-parametric statistics, we're just going to assume in this case that you're dealing with normal data. Statistics helps us determine with more confidence that there's a difference or not a difference. You can still be wrong. We can't necessarily prove it. We don't say we've proved anything. We just say we feel confident that there's a difference here. Larger yield differences are more likely to be significant, but we can still find a difference in half bushel if it's real and if we have enough samples and we can get that variability down. The wider that variability is, the more error you have and the harder it is to prove a difference. If you have a half bushel yield difference, but that variability is tight around each one of those, we can actually prove that they're different. Well, not prove. We can have confidence that they're different, but it's hard to get to that. Are there any questions of anything that I didn't cover? No? All right.